In the last video, we talked about how you could use the area of a velocity versus time graph to find the displacement of an object. And we did this using the constant velocity buggy model. But what we're going to do now is we're going to see if we can't do that with the accelerating particle model. And the one we've been using is the cart on a hill. So let me draw with one of our cart scenarios, and let's see if this makes some sense for us. So here's our ramp, and again, our ramp implies constant acceleration. And we'll talk more about it later, but it's the steepness of the ramp that determines the acceleration. But let's say you started from here. So here's your cart. Here's your position and time graph. And your velocity time graph. There's our zero position line. And so when we look at our cart, right, where is it when we start and what's it doing? So it's somewhere in front of the zero line. Okay, it's somewhere in front of the zero line. But when I look at it, it looks like it's already moving. So let's start with the velocity versus time graph. When I look at the velocity, it's already moving at time zero when I start looking at it, and it's moving to the right. So what does the velocity look like? Well, it has some initial velocity, and it's getting faster in that direction. So I'm okay with this. This looks pretty good to me. What does the position versus time graph look like? Well, it's getting faster, so it has to be getting steeper. But one thing that's important about this is that it has an initial velocity. So when I look here, it's not going to be perfectly flat to start. It's going to be a little bit steep and getting steeper. So if I were to put a slopometer on there, there's the initial slope. And later on it's steeper, so it starts off with a small velocity and ends with a large velocity. And so the question is, when I look at this, all right, how do I go from here to here, and then how do I go from here back to here? Well, we were talking about it in the last video, and this looks like if I want to analyze, go this way, I'm going to look at the slope. That's why I'm using the slopometers. But what about this one? If I want to go back, what do I analyze? I analyze the area. Now, in your calculus class at some point, they're going to tell you, they call this the area under the curve. But area under the curve is a stupid way to say it because, one, this isn't a curve, and it's not necessarily under. It's always you're going to shade the area between your line and the horizontal axis. Doesn't matter what your line looks like. So if you want to do the area thing, you look, you shade the area between your line and the horizontal axis. In this case, I'm going to drop this down. And if I wanted to find the change in position, I would need to get this area right here. So, according to this graph, that would be the change in position. What does it look like on my velocity time graph? So this here is the initial velocity. That's the time. Up here is the final velocity. How do I get the area of this thing here? Well, there's a couple ways. If you look closely, this shape is actually a trapezoid, and so if you knew the trapezoid area formula, you could do it that way, but that's not obvious to me. So I'm going to use this method where I'm going to break it up into a rectangle and a triangle and see if I can't represent those things. So how am I going to find the area of this? Well, let's do the triangle first, and then we'll do the rectangle. So if I look at this triangle, the area of a triangle is 1/2 the base times the height. Okay. So the area of the triangle plus the area of the rectangle. 1/2 the base times the height. The base of the triangle is t. What is the height? Well, the total height is v, but I only want this section here, so this section right here is v minus v0. V minus v0. This represents the area of the triangle. To represent the area of the rectangle is just base times height. T times v0. So what I'm going to do is I'm going to distribute and then combine like terms. These two represent this first one. I'm going to add on this last one. This is interesting because these two are like terms. This is 1 TV0 minus half TV0. 1 minus a half is a positive half. So I have the first term. So these two terms combine to make this term. And now if you notice, each of these has a 1/2 t in here. So I'm going to factor it out. And you're left with that expression. And this is an expression that you get from the textbook. So from the last video, what we realized was that the area is actually the change in the position. This is not an equation you will find on the AP sheet. However, it is a textbook equation and can be super useful. What I like about it is it comes exactly from this graph. It comes exactly from this graph. We're not like making it up. It's not like out of nowhere. It really comes exactly from this graph. Let's continue with this as we go here. So we have a sense that if you want to analyze the slope of the position, you get the velocity. If you look at the area underneath the velocity, you get back to the position. Now, it's important to recognize the fact that you don't actually get the position. You just actually get the change in position. Okay? You just actually get the change in position. We may talk more about that later. But what does the acceleration graph for this look like? Again, the same thing holds true. If I want to analyze the acceleration in terms of the velocity graph, I'm going to look at the slope. Two things I notice about the slope of this velocity graph is it's constant and positive. Therefore, my acceleration is going to be a constant positive. I wonder if we could use our same rationale to look at the area here to get the change in velocity. Because if I go down here, slope to get the next one, slope to get the next one, if I'm going up, I know area here doesn't work here. Let's check. If I drop my vertical down here, and I shade the area, is it going to allow me to get some information about the velocity? I wonder. Let's check. So this acceleration value is A. This time value is t. So how do I represent the area between your line and the horizontal axis for this bad boy? Well, again, it's a rectangle, so base times height. So the area here is equal to AT. And I'm interested, I wonder if that actually represents anything. Well, to really realize this, let's go here and look at our velocity time graph and see if there's a mathematical model to go with this one. It's of the form y equals mx plus b, so let's start there. On the y-axis is our velocity. On our x-axis is the time. Our b value is our initial velocity. And our slope is our acceleration value. Now, right away, I'm noticing AT, and I don't think that's a coincidence. So let's get AT by itself and see what happens. In order to do that, I'm going to subtract the initial velocity from both sides. And this is a statement I'm familiar with. Final minus initial, that is the change. And so it looks like what we're getting down here is something very similar, where the area goes this way again, where if you want to analyze the slope, you can go from position velocity and velocity to acceleration. And if you look at the area, you can go from acceleration to velocity and then from velocity back up to area. Again, it doesn't tell you what the velocity values are, but it gives you a change in the velocity. So according to this, the area of this one, area of the acceleration graph, is the change in velocity.